Hi everyone, in this video segment we are going to be talking about how size can affect acidity and basicity. It is the case that larger atoms will in general possess more acidic hydrogens than smaller atoms. This is because larger atoms can better accommodate the negative charge in the conjugate base. When you have a larger atom, it can more effectively disperse and spread out that charge over its larger valence shell. Okay, that's important. So larger atoms have larger valence shells. There's literally more 3D space for that negative charge to be dispersed. It is less concentrated. And size is going to best distinguish the difference in acidity between two acids when the two atoms bearing the acidic proton in question are different and they are located in the same periodic column. Okay, this is a vertical comparison if you're looking at the periodic table. So let's look at some examples here. We have H2O, we have some thiol, and we have a selenol. And notice I provided the pKa values. Here are the approximate pKa values. The selenol, CH3SEH, is the most acidic at pKa 5.2, approximate pKa value. H2O is the least acidic at pKa 15.7. We see increasing acidity as we go from left to right because the atom that is bonded to the acidic hydrogen is increasing in size. Selenium is the largest. If you looked at the periodic table, in one of the columns you have oxygen, sulfur, and selenium as we go down. Selenium is larger than sulfur. Sulfur is in turn larger than oxygen. So again, let's look at the conjugate base stability to think about relative acidity of the acid forms. H2O is deprotonated to form OH-. CH3SH is deprotonated to form CH3S-, and CH3SEH is deprotonated to form CH3SE-. Okay. Now, we said that the selenium atom was the largest atom, so it has the largest valence shell, and it's most effectively able to disperse that negative. When we are dispersing that negative, we are acting to stabilize the negative charge, that extra electron density that has been accommodated by the selenium atom as it was deprotonated by some base, right? It took on 2 additional electrons from the selenium hydrogen bond. Sulfur, its valence shell won't be as large. Therefore, there's not as much of a capacity for the sulfur atom to disperse that negative charge over its smaller valence shell. And oxygen, we'll say, comparatively has a smaller valence shell than the sulfur atom. And accordingly, that negative charge is going to be more concentrated. Okay, it is going to be more concentrated. If that negative is more concentrated, it is less stable. The negative charge on the selenium atom is going to be less concentrated. It is stabilized. It is dispersed over the larger valence shell. So if you're looking at atoms bearing acidic protons that are located in the same periodic column, we can differentiate the acidity of those species based upon atomic size. Okay, and again, if you're looking at acids, it behooves us to deprotonate them and look at the conjugate bases and ask what factors are playing a role in the stability of the conjugate bases. We have increasing conjugate base stability going from left to right because we have increasing size and thus increasing potential to stabilize and disperse the negative charge.